Hello everyone, and welcome to the fourth reading group. Today we are going to talk about the following paper, Vision Transformer with Deformable Attention, where Shartak, Rolf, Alkamas, and myself will explain to you the concepts and the main ideas behind it. You can go ahead.
Recording in progress.
Transformers presented some good results in the computer vision domain, but state-of-the-art models are showing some limits. If you use dense attention, which means that the current input serves as the input for all the preceding layers, it will result in huge computational cost. On the other hand, using sparse attention or a subset as a small relative, it will lead to data agnostic problems and not a well-learned models. In order to pass those issues, this paper presents a new technique, deformable attention transformer. So let's move to the motivation slide. Transformer-based models have larger receptive fields and excel at modeling long-range dependencies compared to CNN, which make us want to do further research in order to improve it. Most recent work on CNN use deformable convolutional networks and leads to impressive results. And that is what motivates us to do some exploration on deformable attention pattern in vision transformers.
Yeah. So I'll take over since Abdul is actually having some connection issues. My name is Rolf. Sata, can you go to the next slide, please? Hello, Sarthak?
Yeah. So, which slide?
Can you go to the next slide?
Yeah. Can you not see it? So, okay. Let me just try to do it again.
Okay. Yeah, the previous slide, the motivation slide.
Motivation. Yeah.
Yeah. Okay. So now transformer-based models have a larger receptive fields and excel at modeling long-range dependencies compared to CNNs, which make us want to further research in order to improve it. Most recent work on CNN and deformable convolutional networks leads to impressive results and motivates us to explore a deformable attention pattern in vision transformers. A literal implementation is a naive approach because of the higher computational complexity. So the approach presented in this paper will take that into consideration. Next slide, please. Yeah. So so just a brief overview of transformers. Transformers are a deep learning architecture that came into being in 2017, and it is currently the state of the art in the domain of NLP. A transformer can be divided into two main blocks. It contains n number of encoders and n number of decoders. Let's, for example, say that a transformer is a translator from English to French, like the Google Translate. The input is, I want a dog. Each word of this input is embedded or transformed into a vector parallelly. We add a positional encoder in order to get the context. The results are then passed to the multi-head attention block, which is also known in short form as MHA. Then it is fed into a feed-forward neural network, which is then normalized again. Let's name the output of this phase A. So the output of the train set, which is the French sentence, will be embedded and a positional encoding will be added and then passed to a masked multi-head attention and normalized. Here, by masking, what I mean is that the next word of the sentence is what is masked, because that is what the model wants to learn. So this output with the previous output A will go through a multi-head attention again, and then through a feed-forward neural network, where then it will be finally normalized and passed to a linear layer and a softmax in order to get the probabilities. So this is a overview of the architecture of a transformer. Now let's take a deeper look into the multi-head attention model. The input of this Thank you. The input of this phase is query Q, key K, and a value V. We get each one by multiplying the input, which is, as in the previous example, I want a dog, by the weight matrix for each one. So the weight matrix for Q, the weight matrix for K, as well as the weight matrix for V. We then pass each one through a linear layer and a scaled dot product attention. You can see the architecture here. The scale dot production, product attention. We pass each through that. And the formula is after concatenating, the formula is the softmax of Q dot transpose K divided by the square root of the shape of K dotted into V. The results are concatenated and finally passed to a linear layer. Now that we have like a global view of the attention, we can take a more detailed view of how deformable attention can work.
Okay, so
yes, Sarthak.
So I will now taking on then. So I'm Sarthak. So yeah. So after we went through how a transformer network generally works, so we will now take a deep dive into what the authors of this paper have come up with. So existing approaches for vision transformers to address the challenge of excessive attention limits the potential of modeling large objects. So basically, we have to, as you can see in the image, so we have to just go through. So normal transformer goes through every pixel, and every pixel acts as a token for the multi-head attention block, which creates very high computation costs. So thus, data-dependent attention. We need a data-dependent attention to in order to have a flexible approach to what we need. So as we can see, this is a picture of a cat. So we want to know the features of cat only for the object detection of a cat. So we won't be needing how trees are the trees look like or anything. So we want a flexible network which can detect the features of the cat itself. So this can be only done with deformable attention. So implementing the deformable attention module drastically increases the space complexity too. But to tackle this problem, the authors calculate the regions among which the tokens which are basically the input to the multi-attention block. So these are the tokens are like the grids. So for each token there will be a key and value pair. So so using they actually relate each tokens using the guidance of the important regions in the features that we are giving present in the images. So these focus regions are determined using the deformed sampling points, which are learned from the queries using an offset network. So the main focus is on generating offset network. So we'll start on with that. So actually, they use a bilinear interpolation to sample features from the input, and then they project to key and value pairs, which then the multi-gate attention is applied to attend the queries and the keys and values to sample the aggregate features from the values. So to achieve this, they given a feature map of size h, w, and c, where h is a height and width, and c is the number of channels. They uniformly sample a set of h, g, and wg points using an evenly spaced grid of size as shown in the figure. Now, here H refers to H by R being since the gate size need to be downsampled. So to create an input feature map, the factor is they have selected the factor as R. So Hg is equal to H by R and Wg is W by R. So these generate a value of reference points which are linearly spaced 2D coordinates which range from 0, 0 to Hg minus 1, Wg minus 1, and then they normalize these points to the range of -1 and +1 according to the grid shape, in which -1 comma -1 indicates the top left corner of the grid, and +1 indicates the bottom right corner. So after that, when they have done this, then the next we basically obtain the offsets for each reference point. So the feature maps are projected linearly to the query. So as you can see in the image, in the right image, so we get the reference points, and there's a offset network in which we give the weight of the each query points. So the feature maps are actually projected linearly to the query tokens, which is q equals to xwq, and then fed into a lightweight subnetwork offset that we can see on the left side. This is a network that they designed for getting the offsets of each reference points, and they also they try to stabilize the training process by scaling the amplitude of p by some predefined factor s to prevent too large offsets, so that the top offsets can go to too large values. So they try to scale the amplitude by using a scaling factor s, which is predefined, and the product you can see is delta p equals to s into tan h of del p. Now, the subnetwork, they have adopted the subnetwork for offset generation, which takes the query features as an input and outputs the offset values for each grid. So to learn these local features, so you have to just learn the local features and determine how well they are, so to calculate reasonable offsets from the reference points. So they use two convolution layers and a nonlinear activation function, as you can see, is GLU. The input features are first passed through a 5x5 stepwise convolution to capture local features, and then GLU activation function uses a 1x1 convolution to get the 2D offsets of each reference point. Now these are the functions. So the initial sample points that we get are pushed into the in position using the predicted offset that we get from the offset network. Then they are projected linearly as keys and values, which will be the input for the multi-head attention block. And here you can see the function phi is a sampling function which is used for bilinear interpolation. So this is a function which basically does the bilinear interpolation of sample features so that we can get the key and value pairs. And now and the function g is defined here as maximum of 0, 1 minus modulus of a minus b. So if we have 2 points a and b, so these generalize into as g would be non-zero only on the 4 integral point possessed 2. So So this is a general, so this function has a feature like this. So it simplifies the weighted average of 4 locations, which gives an exact value of a particular token in the input. Finally, they perform the multi-head addition on the offset we get, and k and v, keys and value pairs. So yeah, so we have the position embedding. So this is the deformable attention module that they implemented to get better accuracy. Now moving on to the model architecture.
Okay, thank you. So in the model architecture, as you can see, a typical deformable attention block consists of 4 stages. So as opposed to a normal transformer, in this the vanilla multi-head self-attention block is replaced with a deformable attention block. So when we combine it with the NLP, we have a deformable vision transformer block. In terms of the network architecture, it shares a very similar pyramid structure, which is broadly applicable to various tasks. Now, as illustrated in the figure, the input image with the shape of 3 channels is first embedded with a 4x4 non-overlapped 4x4 non-overlap convolution with stride 4, followed by a normalization layer to get a patch embedding. So keeping into mind the hierarchical feature pyramid, the backbone includes 4 stages. So these stages are progressively increasing in the stride. So between 2 consecutive stages, there is a non-overlap 2x2 convolutional with stride 2 to downsample the feature map so that the spatial size is halved and the feature dimensions are doubled. In the classification task, after stage 4, we can just normalize the feature maps and then adopt a linear classifier with pooled features to predict which class are we going to classify it. We can also use this in image detection as well as segmentation tasks. In image, the role this architecture would play in those tasks would be to extract multi-scale features. Like in YOLO, we extract features from by scaling the images multiple times. So we can scale it down as well as scale it up so that it becomes invariant to image scaling. So here, this architecture plays the role of the backbone in extracting those multi-scale features. So now coming back to this model architecture, in this model architecture, in the 3rd and 4th stages, they introduce successive blocks of local attention and deformable attention. What these successive blocks of attention blocks do is the local attention generates the local tokens. So these local tokens, when after generated, are passed on to the deformable attention block. The deformable attention block then takes these local tokens and then generates global relations between these tokens. So this is how the model learns a strong representations. This shares these strong representations share similar patterns to transformers like the point transformer. Now, the first 2 stages over here, as you can see, there are no deformable attention blocks. Sorry. So the reason why there are no deformable attention over here, Sato, can you go to the next slide, please? Yeah. So as you can see in the first table, the authors of the paper tried different architectures of different variants of this block. So they tried to put the deformable attention in each of these stages. So you can see in the line where they put the deformable attention in all the stages, the floating point operations amounted to 4.64 Gs and the accuracy was around 81.7. So progressively, as you can see, the accuracy increased to 81.9 as it was put only in the last 3 stages, then 82 and then 81.4. So the maximum accuracy we could achieve was in the stage where the deformable attention was in only stages 3 and 4. And the floating point operations, which are the number of operations or the model, how many operations the model performs was 4.59 as opposed to 4.64 or 4.6 when we put the deformable attention in other this as well. So this is the reason they put the deformable attention only in stages 3 and 4. This was like a trade-off between the model capacity, which is the capacity of the model, which is the ability of the model to store the patterns. Obviously, if we put the deformable attention all 4 stages, the capacity to store the patterns will be more, but the computational overhead will be way huge. So for a trade-off, they just used this experiment and then put it in stages 3 and 4 only. Also, another reason is the key value pairs in the key and values in the first 2 stages have a very large spatial size. So when we perform the dot products and the bilinear interpolations in the deformable attention, this creates a very large computational overhead because of the large spatial size. So that's another reason why they chose to put it only in stages 3 and 4. So in order to maintain fairness in comparing it to the other architectures, the performance of this in comparison to other architectures, they have made 3 variants of this. As you can see in the second table, the first variant is DAT-T, DAT-S, and DAT-P. What varies in this is the number N1 is the number of blocks at the stage I. So at stage 1, you have only 1 block. At stage 3, you have 3 blocks. At stage 4, you have just 1 block again in DAT-T. And C is the channel dimension. The window size is the region size in the local attention module. Heads is the number of heads in the deformable attention block. And the groups are the offset groups in the deformable attention. So this table basically shows the different configurations they have used and how they have used this configuration in comparing the performance of this model to the other models itself. Okay, this is it for the model architecture. Okay, just a sec. Just give me a second. So now these are the experiments performed with the DAT. Here they trained. Here he took the authors of the paper trained and tested and proposed the VT model on the standard ImageNet dataset, which contains around 1.3 million images and covers around 1,000 classes. The image size during the training was set to 224 into 224. They used the Adam optimizer with cosine learning rate scheduler and also augmented the data. Now comparison with the CNN. Comparing the Vita with both the CNN models and vision transformers with similar model sizes, both achieved top 1 by 5 accuracy, and the real top 1 accuracy on the ImageNet was reported. Can you go to the next slide, please? Yes. So the deformable attention transformer was able to get better attention with similar computational cost to recent models like the VT, Swin transformers, and DCN. The approach was tested on 3 benchmarks: the ImageNet, the COCO, and the ADD20K segmentation. Next slide, please. Okay. Next slide. This is summary. Okay, summary. Yeah, thank you. So in summary, the transformers were able to solve not only problems limited to NLP, as we seen in as we've seen in the example I gave in the beginning, but also computer vision tasks like image segmentation and image object detection as well. Huge models like the VTA generally do better than larger models like the VIT-L and wins against the state of the art. Vision transformers work better on large scale data. So convolutionals are translational invariant, locality sensitive, and a lack of and generally have a lack of a global understanding of the images. So in conclusion, to conclude this paper, next slide. Thank you. To conclude this paper, the vision transformer uses a multi-head self-attention in computer vision without requiring image-specific biases. The model splits the images into a series of positional embedding patches, which are then processed by the transformer encoder. This is done to understand the local tokens, local as well as the global features the image possesses. And this paper is simple and an effective architecture. This can be adapted to both image classification as well as dense prediction task. So it results in a simple yet effective vision transformer architecture named VITA. Extensive experiments show that VITA outperforms representative vision transformers in various respects because of the classification accuracy, data efficiency, as well as the general ability on the downstream task. Thank you. This is the end of the presentation.